Okay, let us begin. So, now I am going to talk about the modeling and numerical simulations of turbulent spray combustion. So, over the last 7-8 days we are listening many topics. The modeling of turbulent combustion, mostly in the gaseous phase. So, combustion takes place in the gaseous phase, but if you are using liquid fuel, the liquid fuel needs to first inject it into the combustion domain, combustion chamber. Then it undergoes the primary atomization, and then it creates filament or ligament, what you call, and then these ligaments again is subjected to the secondary atomization, and then it forms dispersed fine droplets. Okay. So, now these droplets, they interact with the surrounding gas phase. So, how do they interact? I mean, they interact through the gas phase by the drag force, and then there is evaporation. So, there is a heat transfer from the surroundings to the droplet, and consequently there is evaporation. So, after evaporation, that the evaporated fuel mixes with the surrounding air, and then ignition takes place and the combustion takes place. And after combustion there is the pollutant and other things. So, those I mean, this phenomena, I mean, there are, as you can see, that there are multiple activities that is going on since the injection of the liquid fuel into the combustion chamber. Okay. So, this multi-scale, so there is a multi-scale and multi-physics activity, I mean, that is going on in the combustion chamber. So, now we need to effectively model that in our numerical code, and today we are going to talk about these RANS and LES applications of spray combustion, and we will talk about the advanced combustion models, maybe not so advanced, the flamelet model that is there for a long time, and then I will briefly talk about the conditional moment closure method. I think some of the participants are also interested in the CMC method, like the conditional moment closure method. So, I will briefly touch upon that in this presentation. Okay. But before doing that, I will also quickly go through the review of the single droplet combustion. So, that may be useful to understand that how the evaporation is taking place and the time scale associated with the evaporation of the droplets and combustion. So, as you see that we have the more than 50% of the energy that is being produced, that comes from the oil. Okay. So, only the red one is basically the natural gas, and then we have the nuclear energy is only this much, that is growing, of course, and then the hydroelectricity, okay, and coal, okay, coal combustion. Now, what you see that we have a tremendous use of oil in our energy production systems, and that is more or less 50% of the total energy that is being produced by combustion, more than that. So, knowing only the gas phase combustion is only the half of the knowledge about this combustion. So, we need to study that what is going on in the liquid fuels. As you see that the liquid fuels are being used regularly in lot of applications, like the rocket engines, where we can have the liquid fuel that is injected into the oxidizing medium, and also that is commonly used in the gas turbines, okay, and the diesel engine kind of applications. So, in this, the combustion chambers, so the liquid is injected and that is getting atomized. So, after that, atomized droplets are subjected to the turbulent flow within the combustion chamber, and then they disperse, vaporize, and then mixes with the oxidizing media, and then combustion takes place. So, soot and thermal radiations have become important, and then multiple length and time scale. As you see that there are several processes, and each of them contribute different length and time scales. So, they have a multiple length and time scales problem. So, our aim is always to achieve a higher combustion efficiency when you are driving a gas turbine, and reduction in the environment pollution. So, now to know that, we need to know that what is happening physically when the liquid fuel is evaporating and then mixing and burning. Okay. So, if we know that, then we can basically try to control the pollution formation and try to achieve the combustion of the fuel. Otherwise, in some applications that the fuel can escape the combustion chamber without burning completely. Okay. So, now in order to do that, we need advanced computation and modeling and simulations, which will basically couple the different phenomena that is going on, like the turbulence spray interactions, turbulence chemistry interactions, right. So, we need to model those things, and for that we can use different state of the art models that we will briefly describe during the talk. Okay. So, before that we will just point out that what are the current topic of research that we have at this moment. So, a lot of activities are going on in this front, like the injection and then spray processes, right, like the size, velocity and temperature distributions, the profile of average quantities, right, after injection. Then the single droplets, some researchers are involved in the single droplet studies, right, the effect of the transient effects, then the ignition, evaporation, combustion. So, they are basically focusing on a single droplet and then trying to resolve the droplet also and get idea about different processes, the pollutant formation. So, these are the areas of interest in this. So, let us quickly go browse through the droplet combustion. So, single droplet combustion. So, these materials are available in these books. So, okay. So, we have a liquid droplet that is basically subjected in an oxidizing media, and when there is the heat is coming from the ambient to the liquid fuel, and then it is basically the fuel vapor is coming out and the oxidizer is coming from the other side. So, it is basically a diffusion flame that we discussed before in the supplementary lectures. So, the fuel and the vapor, they come into contact, and when they reach a stoichiometric proportion, then we can get a flame here in the reaction zone, okay. And the products are formed in this zone, and then the products can diffuse in either directions, okay. So, it can come it will diffuse inside and the outside, okay. So, inside the flame zone we can have only the fuel and product, right, what we discussed before. In the outside of the flame zone we have the oxidizer and the products, okay. So, this is basically a droplet burning in a convective flow, and that is in a quiescent flow. So, you can see that if there is no flow, the droplet burns in a spherically, it is basically you can model them as a spherically symmetric problem, okay. But in this case, if there is a convection around the droplet, then the flame will not be spherical and it will be little distorted. So, it is a non-spherical flame when there is a convection. So, heat transfer is the main physical process that is basically governing the droplet evaporation, right. So, when you are injecting the droplet, it comes within the domain with a certain velocity, and then heat diffuses in, and then after that there is a evaporation, and you see that after certain distance from the injector it starts igniting, and then there is a first appearance of the flame, and when the flame is, here actually the temperature may not be very large. Suppose you are injecting the droplet at 300 Kelvin into a media that is at 500 Kelvin or 600 Kelvin, okay. So, it may not, the heat transfer may not be very great, but when there is a flame surrounding the droplet, the heat transfer rate increases manifold, okay. So, multiple times it increases, and then you can see that it burns very quickly, okay. So, the key quantity is the heat transfer from the surrounding gas, as I said, that is governing the evaporation. So, now you can see that when the droplet is injected at the initial temperature, let us say T0D, okay, and then this is the droplet radius RD, okay. So, initially there is a discontinuity, right, at the surface of the droplet, okay. So, here the temperature is the T0 infinity, the ambient temperature, and the fuel mass fraction is YF within the droplet, okay. So, this is basically unity within the droplet, and at the surface there is a discontinuity, okay. So, the fuel mass fractions within the droplet should be unity, there is no other things if you can, and then at the surface there is a discontinuity, and then it is basically the surface mass fraction that you can obtain. There is a relationship like Clausius-Clapeyron relationship, So, using that you can calculate the what is the surface mass fraction of the fuel, and at the outside the droplet you see that it goes to the ambient mass fraction. Okay. So, which is basically 0 in many applications. So, it goes to 0. As soon as the heating started, so there is a heat transfer from the ambient. So, you can see that the temperature drop becomes like this, and then within the droplet there is a rise in temperature initially. Okay. So, it starts heating up inside the droplet, and similarly you can see that the fuel vapor mass fraction also increases here, okay, as because of the rise in the surface temperature of the droplet. Okay. So, you see that the fuel mass fraction increases here, and then it goes to some value 0 to the infinity 0 maybe. Okay. So, if you go if this activity goes on for sufficiently long time, after some time it may be uniform temperature within the droplet, that is basically the wet bulb temperature, and then this quantity also increases, as you can see here. So, this is basically the transient effect of the droplet heating. Okay. So, now our aim is to basically calculate the evaporation rate and then the droplet radius or the diameter history, that basically over the time how the droplet diameter is changing, and then time taken by the droplet to evaporate completely. Okay. That we are going to evaluate. So, there are some assumptions which are basically we are considering the spherical burning of droplet in a spherical flame, no interactions between droplets. So, this is basically a single droplet combustion. So, there is no multiple droplet in our system, and we will represent the process by a quasi stationary process in the gas phase. Okay. So, the time derivative basically goes away, and the pressure is uniform and constant, there is no change in pressure, but in many system you can see that there is a change in pressure. So, all these things are not we are not considering. We will be only focusing on the fuel, oxidizer and products. So, represented by the first chemistry, and that is occurring at the stoichiometric surface. Radiation is negligible, and then thermochemical properties are constant. Basically, the Lewis number is unity, that we are making an assumption. No convection around droplet, but later we will see that how convection plays a role in the droplet evaporation. And size is initially d0, temperature of the surroundings T infinity, and oxidizer mass fraction at the infinity is known. So, we will basically calculate the rate of evaporation and the evaporation time and flame position. So, I will quickly go through that. So, this is basically the flame around the droplet. What you can see that the droplet radius is Rs, and the flame is located at this radius Rf. Okay. So, this is the flame radius. So, one of the solution will be the flame radius also from our analysis, and inside the flame we have only the fuel. So, this is the fuel distributions within the flame. Okay. So, there is no fuel in the outer region of the flame, this is the inner region of the flame. In the outer region we have the oxidizer, that is basically coming, and it is almost 0 in the flame front. In the flame front we are producing products. So, this is the maximum mass fraction of the product that we have in the flame radius, and then it is diffusing in the both sides. Okay. Same thing about the temperature. The temperature is the surface temperature here Ts, and then it goes to the Tf, that is the flame temperature. So, we can calculate Tf, what is Tf, and then it decreases to T infinity. So, when there is a flame, you see that there is a increase in the heat transfer, because the gradient becomes very steep, right. In the absence of flame, suppose the droplet is evaporating with in a hot environment, but much less than the flame temperature, right. So, T infinity. So, now you can see that gradient is very small, right. So, we see that the evaporation the combustion, the flame basically plays a dominant role in the droplet evaporation. So, we will start with the governing equation in a spherical coordinate system. So, first one is the mass conservation equation, and so this is the form if you neglect the del theta and del phi terms. So, this is now you can obtain this as a solution of this. So, what do you see that the mass flow rate is independent of radius, right. So, this is basically the mass flow rate. If you multiply it with by 4 pi factor, then it is mass flow rate, it becomes mass flow rate, that is independent of radius. Okay. So, that means the evaporation rate m dot f is also a constant. Now, we write down the equations, species conservation equations for individual species like fuel, vapor and oxygen. So, these are the equations with, and they have the source terms, right. So, same thing about the energy equation, we write down the energy equation in the spherical coordinate system, and from our stoichiometric knowledge of the stoichiometry, we know that the omega dot f and omega dot x are related by this. So, we can basically use this relationship here and simplify, and q dot is the heat release term, that is basically omega dot f multiplied by heat of combustion, right. So, here we have basically the boundary conditions, okay. At the droplet surface we have the boundary conditions, and then the fuel. So, this is the mass flux, okay, mass flux terms, and then the energy equation. So, these are the boundary conditions we have. So, I will quickly go through this, and then finally you can basically solve these equations. So, let me go through this slide very fast, and if you integrate these equations and apply the boundary conditions, so at r equal to infinity we have this parameter b. So, parameter b we have, it could be different based on your equation that you are considering, right. So, this is basically just take a minute. Okay, so these are the transfer number that we have formed, and then we have to solve these equations. Okay, so if you solve them, and then it is a quite long process. So, and finally you will be able to get the evaporation rate. So, this is the rate of the expression of the evaporation rate. So, as you see that the rate of evaporation is function of a number, that is Spalding number b. So, it is a proportional to log of 1 plus b, and also the rho d, right, the mass diffusivity, that also plays a role here, and it is also dependent on the droplet radius. Okay. So, these are the Spalding numbers if you consider based on the oxidizer temperature and the fuel and oxidizer. So, fuel and oxidizer together, and fuel and the energy equation basically temperature together, or oxidizer and temperature together. So, these Spalding numbers are basically derived from the conserved scalar, right. So, we have defined the conserved scalar, and then it is basically a normalized form, right. So, b infinity minus bs. So, b is basically the conserved scalar that we are talking about. So, if the Spalding number is b infinity minus bs. So, infinity is the far field and s is the at the droplet surface. Okay. So, from the definition of this this parameter b, you can obtain this relationship, right. So, this is the rate of evaporation, and we can basically calculate that what will be the rate of evaporation if we know the Spalding number, right. For Lewis number unity, this should be equal, right. So, both the the species and the energy, they are diffusing in the, they have the same diffusivity, right. So, thermal diffusivity is equal to the mass diffusivity, and then you can have this relationship. So, how do you calculate? So, we assume the droplet surface temperature Ts, and then we estimate YFS from the Clausius-Clapeyron relationship, and then using basically this Ts we can calculate this, and then check whether we satisfy this condition. If not, then we iterate, and if we are converged, then we know that what is Ts and what is YFS, everything, and then probably we can calculate the rate of evaporation. Okay. Pardon? So, it is a first chemistry, it is a flame sheet assumption, like fuel plus oxidizer is going to product. So, from the heat balance at the interface, and at the surface, at the flame surface, you can basically calculate the flame temperature and the flame radius. So, everything will be in the slide. So, I am not spending much time on this, but if you are interested, you can see these slides, or you can refer to the book by turns. Okay. Okay. So, this is a relationship between the flame radius and then the flame and the droplet radius, right. So, RF is the flame radius and RS is the droplet radius. So, we can derive a simple relationship like this. So, this is a function of the Spalding number, and then the oxidizer mass fraction at the infinity, and then the stoichiometry ratio. So, if you know all this quantity, then you can calculate what is the flame radius. Okay. So, typically for a benzene burning in air, so we have a stoichiometry of 3, and if Y oxidizer at infinity is 0.233, then you can basically calculate the flame radius. So, the ratio of the flame radius and the droplet radius is around 27 in this case. Okay. Now, you can also calculate the droplet diameter history. So, when you know the rate of evaporation, you can write down the conservation equation of the liquid droplet, right. So, this is the change in mass of the droplet diameter, that should be equal to the rate of evaporation rate minus of the rate of evaporation rate, right. So, now if you express that, and you have to write down the MD in terms of the droplet radius, okay, and then you can form this equation and then you integrate it. So, then this k is basically a constant, which is nothing but this term, okay. It is a function of the Spalding number. So, if you know this constant, then you can calculate different thing. So, suppose you know the initial droplet diameter and you know this constant k, okay. So, you can calculate what will be the droplet diameter at some time interval, okay. Also you can calculate the droplet lifetime. So, the droplet lifetime is the time taken by the droplet to evaporate completely, okay. So, you put 0 here, right. So, when the droplet has completely evaporated, so you put 0 here, and then you can calculate the time taken by the droplet to evaporate, that is, it will become d0 square by k. So, d0 is the initial droplet diameter, okay. And if you carry out the there is a plot of that is obtained by the experiment. So, you see that we have basically this slope. Now, this is basically the diameter square that we have plotted, okay. In the y axis we have the diameter square, in the x axis we have the time coordinate. So, we see that the slope is constant almost, except probably here in the initial period where there is some transient effect, but otherwise the slope is constant, and that slope is basically this minus k, okay. Okay, so effect of convection. So, suppose there is a convective flow around the droplet, then we would expect that the droplet will evaporate, there will be much more heat transfer to the droplet, and the droplet will evaporate fast. So, what happens in presence of the convection, so the flame has shifted towards the droplet, okay. The flame has shifted towards the droplet, okay. So, this is the temperature distribution now with convection, and this dashed dot line is basically the temperature distributions without the convection. So, what you see that initially the gradient used to be like this, and now it has become steeper, okay. Same thing happens to the fuel mass fraction. So, initially the fuel mass fraction distribution used to be like this. So, now the flame has come inside and it has become steeper, okay. So, the effect of the convection is basically the increase in the heat transfer rate, and then we see more evaporation. So, there is a simple analysis. So, you can represent, you can calculate the rate of evaporation in presence of convection. So, for that you can assume the film radii, that is a thermal film radius, and this is basically the mass based film radius, okay. So, we expect that there is a initially what we did, we placed the boundary. So, this is the droplet, okay, and infinity is quite far from the droplet, okay. So, this is the infinity, okay. So, now when there is a convection around the droplet, this infinity is basically shifting towards the droplet, okay, and now it is not at infinity, it is occurring at a r equal to delta t or delta m, okay. So, whatever boundary conditions you are applying at the infinity, that Y oxidizer at infinity is equal to 0.233 or something like that, that will now occur at Y oxidizer at delta m, it should be 0.233. Okay. So, the effect of the convection is basically this infinity has shifted towards the droplet, and it is now occurring at the film radius. Okay. So, that is delta t or delta m, and we have a relationship like this. So, in terms of the Nusselt number for the thermal radius and Sherwood number, SH is the Sherwood number. Okay. And from the experiment, if you carry out the experiment in a quiescent medium like a spherical, you can start with a sphere in a quiescent medium, okay, and you can calculate the Nusselt number distribution, that will be 2, right. Now, if you subject this sphere and there is a convective flow around the sphere, then you will be getting another expression like this. Okay. So, this is the effect of the forced convection that is taking place around the droplet. Okay. So, it is in the absence of the forced convection, this term will be 0, there is no flow, RE will be 0. So, you recover essentially the Nusselt number equal to 2. Okay. So, when you do the analysis for the convective medium, so we can just modify, you can derive the expressions for the evaporation rate, but it is very easy. So, whatever evaporation rate you obtained without convection, you just change that by a factor of Nu by 2, okay, and then you can consider the effect of Nusselt number. In that case, the Nu will not be 2, it will be more than 2, right. So, depending on the Reynolds number and Prandtl number. Okay, so here is the analysis for this. So, I will skip that. So, finally, your rate of evaporation is basically this, and if you recall, earlier you got the rate of evaporation is 4 pi lambda Rs times log of 1 plus B. Okay. So, now this 4 factor has become 2 and there is a factor Nu. Now, if Nu is 2, then you recover the same expression what you derived before. So, some of the real world effects on evaporation is the variable properties like the gas phase thermophysical properties, thermal conductivity, diffusivity and specific heat. They are dependent on temperature, as we have seen already. So, and the composition also. So, now you need to account for this, you need to calculate these properties at certain average temperature. Okay. So, that average, what will be the average temperature? So, at the droplet surface it is Ts, and if you go to the flame it is Tf, right. So, it could be from 300 to 2100 or 2200. So, that is the range what you have, but now you need to calculate these properties at certain average temperature. So, there is 1/3 rule that is available in the literature. So, people use that and evaluate these properties at a mean temperature. Okay. If you calculate this property at the droplet surface temperature, then the result will be wrong. If you calculate it at a very high temperature, the flame temperature, then the result will also be wrong. So, you need to consider mean appropriately, you have to consider that. So, unsteady effect of fuel vapor accumulation. So, this results in the unrealistic large flame stand of radius. So, it deviates from the Dispersed law. So, droplet heating. So, evaporation rate depends on the time varying temperature field. So, the temperature field, if it changes time to time, then the rate of evaporation will also be changing. Okay. So, multi-component fuel. So, whatever fuel we are using now, they have several components. So, so far we have analyzed only for the single component fuel. So, this multi-component fuel can also be, it needs to be considered in our analysis. So, interactions among multiple droplets. Then supercritical droplet combustion. So, suppose your pressure is greater than the critical pressure, then what will happen, that latent heat of vaporization becomes 0 when P is greater than P critical, okay, and then the evaporation rate becomes infinity, right. So, droplet is suddenly it will evaporate. Okay. So, these are the things which we need to which are basically different than what we are doing so far. The radiation, so radiation increases overall heat transfer at the droplet surface. So, if you have a flame, so then the flame is probably, we are only considering the heat conduction, but then the radiation also needs to be considered. Internal circulation, right. So, the droplet, suppose we have a droplet. So, if you dissolve the droplet, then you can see that there are basically 3 regions. So, within near the droplet surface we have a boundary layer region. So, you can just approximate it like a boundary layer flow, and here and inside that we have a counter rotating vortices like Hill's spherical vortex, okay, and then we have a wake region. Okay. So, now this play a dominant role in the transient heating of the droplet. So, so far when you are doing the spray combustion, we are modeling, sometimes the model can predict the transient heat up of the droplet, okay, but these effects can also be important. Okay. So, most of the models they do not consider these effects. Okay. So, these are basically in the research domain. So, people have done some research and they found that this vortices and then the flow around within the droplet like the internal recirculation, that can also affect the droplet evaporation. So, now I will go to the spray combustion. So, what you see that here we have a schematic diagram. So, we have an injector and we are injecting the liquid fuel here, and it is subjected to, so here is a jet coming here. Now, this jet is basically forming the ligament and then the primary atomization takes place. Okay. So, it breaks up into the small chunk of liquid and then that is the primary atomization, and after that they are also subject to the secondary breakup. Okay. So, that secondary breakup is dependent on by the surface tension force, right. So, that we will see that the secondary breakup, and then after that this droplet is also subjected to the aerodynamic drag that is experienced by the droplet. So, the droplets can collide together. If it is very dense, the collision becomes important, and coalescence. So, after collision they can move back, right, or they can collide and coalesce. Okay. And then there could be turbulent dispersion. Okay. So, if there is an underlying turbulent flow, the droplets will try to follow the smaller droplet will try to follow the gas phase, but the larger particles, if the larger diameter droplets, they find it difficult to manage with the turbulent flow. Okay. Evaporation. So, the droplets that those are getting formed, they will evaporate and release the fuel vapor, okay, and then this fuel vapor mixes with the air and ignite, combustion can take place. So, in a real turbulent spray flame, these complex physical processes occur simultaneously. Okay. And dealing with all these complexities and their interactions poses a tremendous modeling task. So, what we need to do, we need to consider all of them, but it may not be physical. Suppose you are trying to develop a model, so we need to isolate some of the complex physical process. Okay. So, suppose you are dealing with the model of turbulent combustion, then probably it is a better idea to not to attack the primary atomization, secondary atomization process, and then the collision and coalescence. We can take it isolation, we can study the turbulent combustion in isolation, we can only study the droplet drag, evaporation, dispersion and combustion. Okay. So, these parts we can isolate, right. Similarly, if you are interested in the atomization problem, then it is a good idea to isolate the combustion first and try to come up with a model of atomization. Okay. So, those are basically different strategies that we can adopt. Yeah, this is a liquid jet. No. Inside there is a liquid jet, and then the liquid jet will form a ligament. Okay. So, the very large chunk of liquid, okay, it will break up. It will eventually break up. It takes certain distance to break up. Okay. So, inside it we have a liquid jet. Yeah, sometimes that depends on the process what we are doing. Sometimes you can have a well atomized flow at the exit, then it basically saves our life. I mean, we do not have to consider, because this primary atomization and secondary atomization, they are very crucial things, and we do not have a proper, we have some models, but it is very difficult to predict those things. So, that depends on the operating condition. So, what is the pressure drop, right, from the injector to the chamber, and those are the critical things that will govern the primary atomization process. And the diameter also, diameter of the nozzle, right. I have not used any nozzle, so I have dealt with the, so I am just introducing it to the difficulties, but finally I will come to the this part. So, the atomization part I have never looked at it. So, I will focus on the turbulent combustion part and the spray turbulence chemistry interactions, not the atomization of the liquid jets. So, turbulent dispersion is basically you have a turbulent flow field and then the droplets are there. Okay. So, the droplets will try to catch up with the turbulent flow, right. So, when you have the smaller diameter droplet, they find it very easy to cope up with the underlying turbulence. So, they just follow the turbulence, the turbulence. Okay. But if you have larger particles, they cannot. Okay. Yeah, so this is basically a diagram where you see that after from atomization to turbulent spray combustion, there are different physical processes like the spray formation, and then we have the two phase coupling, then wall impact, coalescence, collision and breakup. So, this is one aspect. Then we have the evaporation of the liquid fuel. So, it depends on the gaseous fuel topology, evaporation rate and then liquid mass evolution. Okay. The mixing, so mixing of the evaporated fuel with the gas phase. So, the mixture fraction fluctuations, dissipation. So, these are the different sub processes that is basically present. Then evaporation source term. So, after evaporation there is a source term that we add in the continuous phase, that is the gaseous phase, and then we have the combustion. So, we have many interactions like turbulence chemistry interactions, and then the extinction of the flame, we have the soot, NOx and radiative effects. So, all these processes are very complex. Okay. So, sometimes the modelers like us, we isolate some of the complex physical activities and try to focus on some aspect of the processes like the turbulent spray combustion. Then we will not bother about what is happening here in this side. We will only focus on the spray combustion. But then it may not be a very general model, it may be limited to a particular setup of problem, but we hope that this spray combustion model, it will be applicable to the other problems when you consider everything together. So, the modeling challenges. So, modeling challenges, a summary is given here. So, polydispersity of the dispersed phase particles or droplets introduces a range of length and time scales. Okay. So, when you inject a liquid into the combustion chamber, we are producing large diameter variation within the droplet. Okay. And that is basically the polydispersity, right. So, we have fine particles and we have very large diameter particles also. Okay. The range of particles, and that is basically introducing a large length and time scales in our problem. Interactions of these polydispersed particles with the carrier phase turbulence, that is inherently multiscale in nature. So, turbulence, as you already seen, that it is multiscale in nature and it presents further modeling challenges. Okay. So, particle volume fraction in conjunction with the level of particle fluctuating velocity determines the relative importance of advection transport to collisional effects. Okay. So, the PDF of velocity could depart significantly from the equilibrium Maxwellian distribution. So, these nonlinearities, multiscale interactions and non-equilibrium effects lead to the emergence of new phenomena such as preferential concentration and clustering. So, what will happen? The droplets try to follow a preferential path and they try to get clustered. Okay. They can, so some particles can come very close to each other and within the region there could be the lot of particles. Okay. Now, when there is a lot of particles, when they try to evaporate, locally there could be a very rich mixture, and now you know that when there is a very rich mixture, then that will lead to soot when it burns, right. So, you need to probably know that how to avoid these situations within your combustion chamber. Okay. So, there are different models, like suppose you want to simulate the spray combustion. So, Eulerian approach is one, and then there is a Lagrangian Eulerian approach. So, Eulerian approach, we basically treat both the phase as continuous, okay, and then there are different like two fluid approaches that represent the average size and average velocity of the droplets, and it is mostly suited for the dense flows. Okay. where the volume fraction is typically greater than this 0.001. Okay. But Lagrangian and Eulerian approach, we are treating the gas phase as the continuous flow, that is basically the Eulerian approach, and the liquid particles are represented in the Lagrangian manner. Okay. So, we treat the liquid droplets as Lagrangian particles, they can evolve as per the set of equations within the domain. Okay. So, transport equation of the droplet distribution function or number density function is solved, and it is applicable for the dilute flow where the mixture fraction is small. Okay. And we assume it is the point particle with a point particle assumption. So, what is point particle assumption, I will illustrate later. So, in point particle assumption, basically we assume that the droplet is subgrade. So, the size of the droplet is very small compared to the size of the mesh that we are resolving. Okay. So, then the whatever source term is adding by the liquid droplet to the gas phase, that is basically a point source. Okay. So, it is mostly used in industrial and academic configurations. So, this is quite popular, Lagrangian Eulerian approach, it is quite popular. Eulerian approach has some drawback because you need to capture the interface between the liquid and the gas phase, and that is quite difficult here. Okay. Also, you need to apply the proper boundary conditions at the interface between the liquid and gas phase, right. So, we need constitutive relationships for this application of the boundary conditions. So, that is quite difficult in this Eulerian approach, but it is easy to code and it is easy to parallelize, but where you have a lot of particles in your system, then you need to track it throughout the domain, and you can expect significant difficulty from parallelization of the code. Okay. So, that is quite challenging in the Lagrangian Eulerian approach. So, some of the comparisons are given here. Okay. So, I will talk about the dispersed phase model. So, dispersed droplet distribution function we define. Okay. It is such that so this is the probability of having the particles within diameter range dr at a special location dx and with a velocity dv. Okay. So, this is the distribution function fj, and then this is the total probability of having the the droplet within this range, within the range of diameter radius within the range of radius dr, and then the spatial location dx, which is basically 3-dimensional space, and then the velocity, the 3-dimensional that is also. Okay. So, this is the probable number of particles of chemical composition J. Okay. So, if you are talking about multi-component droplet, then this will come into picture, otherwise you can just drop this J in the radius range r to r plus dr, located in the spatial range dx centered around x, and with velocities in the range of dv around v at a time t. Okay. So, now if you try to reduce the form of this, so if the velocity dependence of the droplet distribution function is not of primary importance, then we can integrate it with the dv, then we can get another set of distribution function. Okay. Then in this distribution function, the dependence on v is dropped, so only the dependence on r, x and t will be retained. Okay. So, Gj represents the number of droplets of the jth component unit volume per unit range of radius. So, that is only the unit volume and unit radius. Okay. Similarly, if you integrate over the physical space, then you can get another distribution function fj, but that will not contain the dependence on the spatial volume and then the velocity also, right. So, these are the some of the techniques. So, initially you can, you should try to have a more general form, but it may not be possible numerically to solve for these distribution functions, that will be computationally challenging. So, we simplify our life, and then we can come up with a reduced model like fj here. Okay. Then you can try to write a transport equation for this DDF, whatever we described before. So, if you assume that they are dependent on the spatial locations and the velocity, then this is the transport term that we get, right. the total derivative kind of thing. Okay. That includes both spatial volume and the velocity. Okay. And then this is the change of radius. Okay. We have seen that f is basically a function of radius, spatial location and the velocity, then all this gradient will come into picture, right. So, this is the gradient in the spatial locations, gradient in the velocity, and this is the gradient in radius, right, and that is equal to the collision term and the breakup term. Okay. So, now this DDF will be subjected to the collision term and the breakup term, because the droplets are colliding with each other and they are also undergoing a breakup. So, if you are dealing with a dilute spray, then the collision and the breakup term will be 0, then we can have 0 on the right hand side, and the simplified form could be like this. If you change the temporal change of DDF is neglected, then we can get a simplified form. So, this is the Williams form for the spray equation, and now we can have different models. So, the dilute spray models, so we can have locally homogeneous flow models, and then we can have separated flow models, and we can try to solve the transport equation of the DDF and try to get solutions like this. So, most famous models is basically the stochastic separated flow model, which assumes that there is a finite slip between the two phases, like, so the gas phase and the liquid phase are within your Dove system, and there is a finite amount of slip between the gas and the liquid phase. Okay. Also, there is an interface transfer rate. Okay. So, the droplet is evaporating and it is adding a source term into the gas phase, right, and then there is a drag force also experienced by the droplet. So, there is an interface transfer rates, and the effect of turbulence on droplet dispersion and interface transfer rates are considered. Okay. But there is another model which neglects this these things. So, the droplet dispersion and the interface transport are not modeled here in deterministic separated flow model. So, these models are quite old, and I think the stochastic separated flow model is very popular among the researchers. So, in stochastic separated flow model, this classical approach is most popular among different dilute sprays model, originally developed in the context of RANs. Okay. So, this model has been developed in the context of RANs. So, we basically consider the finite slip between the liquid and droplet. In the other model, I think the slip is also being neglected sometimes, but here we consider the finite slip and the interface rate, transfer rate. Effect of velocity fluctuations are considered on droplet dispersion, right. So, the gas phase velocity is changing, okay, due to the turbulence, right. So, you need to model instantaneous gas phase velocity from the mean gas phase velocity which you have solved, right. Your CFD, our CFD code is giving the mean velocity, whatever be it, I mean the Reynolds average or Fabry average, whatever, but you need to calculate instantaneous velocity. Okay. Okay. So, that is the challenge that we have here, but it can be, if you are considering the gas phase equation, the turbulence model is K epsilon model, then from K epsilon information you can calculate this Uy. Okay. If you assume that if you are computing the turbulent kinetic energy K and then 2/3 K, right. Okay. So, this will give you the I think square root of 2/3 K. So, this will be your fluctuating velocity at any point of flow. So, if you know what is turbulent kinetic energy, you can calculate the U prime there at that location. Now, this gas phase, now there is a cell in your CFD domain, and there could be different particles, right. So, these particles will see U min, right, and then there is some U prime. Okay. Now, if you give all the particles same U min and U prime, then they will follow the same trajectory, right, but that we do not want that. So, it will not mimic the exact physical process. So, what you need to do, we can calculate this instantaneous velocity based on a normal distribution. Okay. So, we can assume that the mean is represented by the U bar, and the RMS is basically ui, okay, or u prime. I think this is u prime. Okay. So this is the mean, and this is the RMS of the normal distribution that we have, and then suppose your mean is, so this is a normal distribution, this is having a mean u bar, and then RMS is u prime, and then from this you can sample the instantaneous velocity. So for example, this particle may have this velocity as the instantaneous velocity, gas phase velocity. So this particle can see this as the instantaneous gas phase velocity, and this particle probably sees another velocity. Okay. So that is the logic that we use. Okay. So ultimately we compute the mean velocity field and the mean kinetic energy, and from that we calculate the RMS velocity, and we sample it from the normal distribution. So this is the gas phase velocity that this particle sees. Okay. So every particle within this CFD cell can see different instantaneous velocity, which is having a same mean and same variance or RMS. So that is the logic of this stochastic separated flow model. So it models the fluctuations in the velocity field by the turbulence, but the classical model did not consider the fluctuations in the temperature and the species concentrations. Okay. So it was developed in the 80s, but after that there was no study on the effect of fluctuations in temperature and the species mass fractions due to the turbulence. Okay. So that is one of the drawback. So it considered the velocity fluctuations, but the heat and mass transfer rates are neglected. Okay. So as we know, in the turbulent flame, you have seen a lot of demonstrations by Professor Poinsot. The temperature and the species mass fractions vary wildly with turbulence, right. So it is logical that your model should also have the effect of the fluctuating temperature and the fluctuating concentrations, right, because we have seen that the evaporation rate depends on the Spalding number, which is a function of temperature and the species concentrations, right. The classical model used mean temperature and the mean concentrations and evaluated the evaporation rate, but ideally we should calculate instantaneous temperature and instantaneous concentrations, and then utilize that in the Spalding number expression and calculate the evaporation rate. So like what we are doing for the velocity. Okay. So one of the disadvantages is that the local turbulence is assumed as isotropic. That is one of the assumption, and that is why we are using this expression, right. So what happens in the Lagrangian Eulerian modeling approach? So we represent the liquid phase by let's say 1 million of spray particles, okay, and then we track them. We track individual droplet, location, velocity, etc. Okay, and for the gas phase we solve the Navier-Stokes equation. But it is very difficult to track the million spray particles, and then we simplify this. We represent a group of particles, right. We can club some of the particles which may have initially identical properties, like the identical diameter, identical velocity, identical location. Then we can club them and we can reduce the number of particles. Typically we can come down from that number to, let us say, about 1000. So basically we are not now tracking all these particles. What we are tracking is these particles. So that is again one kind of discretization. So in Eulerian gas phase we are discretizing our domain into some finite mesh, but here also we are doing not in the mesh, we are basically discretizing in the number of particles. Okay. All of them, yeah. All of them, the identical velocity, identical location, identical size, identical shape, and then at the inlet, and we mark them together. We can club them together. Let us say these are basically called parcels, and each parcel can contain hundreds of droplets with the same properties, right? Or maybe there could be some, I mean, you know, this is just like a discretizations in the particle space. Okay. You can increase the number of particles and carry out the simulations and see, just like the grid independent study, that what is the effect of increase in number of particles on your overall results, okay, that you can study. Actually, when we are injecting the droplet, we club it together and we say that this many particles have identical properties and I am sending them as a parcel, and then these parcels will remain as it is, altogether they are flow in the domain, right. So, we will track this parcel from inlet to outlet.
In time, inside the parcel, inside a particular parcel, initially we have defined that radius, velocity, etc. would be same. In time, inside a particular parcel, they can change?
No, we are assuming that they are not changing. So, whatever is changing, all the particles are changing accordingly.
All the particles
are
changing similarly?
Right. Yeah. So, there is no difference between the individual droplets within a parcel. They have the identical properties throughout the inlet to outlet. Okay, so continuous phase model, we can fully dissolved, we can have fully dissolved DNS, where we can resolve also droplet and particle, okay, but that is very difficult, right. We can have a very few particles and then we can try to put a mesh within the droplet and try to solve them. So, that is very difficult. So, we can have point particle DNS. Suppose you are doing a DNS, we are assuming that here actually you are trying to dissolve. So, that is fully resolved DNS, but you can do some DNS where you do not resolve the droplet, right. Your mesh size is larger than the droplet size. In other term, the droplet is subgrid. So, droplet size is less than the grid size. So, that is basically the point particle DNS. You can have point particle LES also. So, in here also the droplet size is subgrid, so less than the droplet the mesh that you are using. Also you can use the RANS code, okay. So, depending on the complexity you can have DNS, LES or RANS, and we will show that the equations later on. Okay, so coupling between phases. So, we can have different way of coupling. So, one way coupling where basically the fluid phase influences particles via drag and turbulence, okay. So, these droplets are subjected to the drag and turbulence. So, there is a one way feedback to the droplet. There could be two way coupling, okay. So, here the droplet is interacting with the gas phase via drag force and the turbulence, as well it is releasing the vapor to the gas phase. Basically, it is adding source in the momentum and the energy equations and the species conservation equation. So, that is the two way coupling where two way interactions are happening between the droplet and the gas phase. Also, there is a four way coupling where you can see that in this the droplets are not interacting with each other, but here actually they are interacting with each other. If you have a dense flow, then the collisions and the coalescence and breakup, those become important. So, that is basically four way coupling what we are considering. So, here is a diagram. So, based on the volume fraction you can and the Stokes number. So, Stokes number is basically the ratio of the this tau d. Tau d is the time. So, this is basically the drag force that we have, okay. So, time scale, okay, and this is the turbulent time scale. So, ratio of this is Stokes number and this is the volume fraction. So, if you have, you can use one way coupling in this zone, okay. So, there is negligible effects of turbulence, okay. So, now in this zone when your volume fraction is between 10 raised to minus 3 and 10 raised to minus 6, there could be two way coupling, okay. So, if the Stokes number is less than 1, then the particles decay turbulence, okay. So, that whatever turbulence initially you have, that will decay if you have a two way interactions, and if the Stokes number is more than 1, then the particles enhance turbulence. So, these are the two domain that we have, and then we can have the 4-way coupling when your volume fraction is very large, more than 10 raised to minus 3, then we can have the 4-way coupling. The interparticles effects then become significant. So, particles will interact with each other, like the effect of collision, coalescence and breakup become important there. Talking about the turbulent combustion part and the turbulent spray combustion part. So, I will skip this part. So, these are the atomizations. So, you know that in some applications the atomization also becomes important, and then you have different models to take care of that. So, I will basically not go through that. Then the droplet breakup also. Then particle interactions, what I said, the collisions and coalescence. So, there could be different collision modes. So, they can come and collide and come back, okay, and then the particles can come closer to each other, and then there is some change in mass, right. So, initially in this particle there could be n1 number of particles and it could have n2 number of particles, but after collision the total mass will be conserved, but n1 and n2 will change. So, it could be n1 dash and n2 dash. So, all these things are possible, and that you can take care through the Lagrangian particle modeling, okay. The particle wall interactions, so there are different things. So, suppose in the diesel spray the spray can come and hit the wall, and then depending on the scenario you can have different things like escape and then the deflect, and then the particle can get trapped, okay. So, I am not going into that, there are fairly detailed models available. So, the droplet drag, so, okay. So, this is the change in droplet velocity, okay, and this is the drag force that is the droplet is experiencing, right. So, this is the drag force, and then there could be the gravity force, right, when the gravity is important, and then there could be additional forces due to the several factors like the pressure gradient, thermophoretic effects, and then the Chapman lift, Brownian motion, all these things. So, in the we will mostly consider in the numerical work, we mostly consider the drag force, okay, which is basically expressed like this. So, CD is the coefficient that we need to calculate. So, for a spherical droplet we can have a dependency like this. So, if your Reynolds number is less than 1000, you are using this expression, and if it is more than 1000 then it is a constant, okay, 0.424. Again, for the dense sprays, if we are dealing with the dense spray, then you need to correct the CD coefficient, and then there is a volume fraction term theta, okay. So, depending on the volume fraction your expression will change. Also the spherical, we are talking about the spherical droplets, but if the droplets are not spherical, okay, then you can calculate the eccentricity of the droplet, and then from that you can calculate the CD coefficient. So, droplet evaporation models. So, basically this is the rate of evaporation expression, and that we have already seen. So, there are different models like infinite conductivity model, so which is assuming that whatever heat is being transferred, that is consumed by the droplet instantaneously, and it is going to a different temperature, right, okay. So, this is the heat that is coming in, okay, from the surroundings to the droplet. This is the heat that is utilized by the droplet to evaporate the fuel, okay. So, m dot HFG is the latent heat. So, this is the total heat that is coming to the droplet, this is the latent heat that is taken away by the vapor, and then the difference is being utilized to heat up the droplet, okay. So, this is the change in droplet temperature with time. So, mostly I have used this model, infinite conductivity model. If you want to calculate the finite conductivity model, the droplets have finite thermal conductivity. If you want to utilize, then you need to solve the transport equations of the energy within the droplet, but that I have not done, and mostly people are not doing that, they are sticking to the infinite thermal conductivity model, okay. So, a summary of the droplet evaporation models is available. Now, the droplet turbulence interaction model, right. So, that is what I said that, so if you know the mean and the variance, you can construct a normal distributions, and from that you can sample the instantaneous gas phase velocity, right. So, it is explained here. So, these are turbulence time scale. So, the turbulence time scale is taken as the minimum of this expression, and you can, depending on the mean and variance, you can have different options available. Okay. Suppose this mu is the mean velocity and the variance is the RMS of velocity, and then you can construct the normal distributions and extract the instantaneous information from that. Okay, the turbulent combustion models. So we have so far we have come across different models. So the direct closure is not suitable, right? We have already seen that why it is not suitable. Then we can have eddy breakup or eddy dissipation model. We can have the presumed PDF model. All these models we can employ in our code in transported PDF conditional moment closure method. So they have different complexity, and we have seen that how they perform in different cases. So I am not going into the details. Okay, but I will quickly summarize that what are the challenges of turbulent combustion models when there is a phase change. Okay. So conventional definition of mixture fraction is not conserved for sprays. Okay. So when you are dealing with the spray, your mixture fraction will not be conserved, because mixture fraction will have a source term due to the evaporation of the liquid droplet. Now the question is that whether can we apply the conventional models in our case. Okay. That is the biggest question for the spray combustion. So can we apply the conventional flamelet model, conditional moment closure method, all these things in the spray combustion. Okay. Basically the presumed PDF approach can we use directly. Okay. Because now the mixture fraction is having a source term due to the evaporation of the fuel. The modeling of the two phase source terms in the transport equation for the mixture fraction variance. So now you have previously seen the transport equation for the mixture fraction variance. Now when there is a evaporation of the liquid droplet, there will be a source term. Okay. We will see that how it looks like, what is the form of the source term, and then how can we model that. So that is another key question. Okay. So we will talk about that. The modeling of scalar dissipation rate in two phase flows, and when you are dealing with the conditional moment closure method, you need to have a modeling of conditional scalar dissipation rate and evaporation terms in CMC equations. The modeling of envelope flame between the droplet and the surrounding gas phase. Okay. Most models do not consider the envelope flame, right? Okay. So as I said that this is the instantaneous species transport equation which is having a source term, right? So for practical purposes we average this and calculate the we get the transport equations for the species, and there is a chemical source term which is basically averaged. Now it is highly nonlinear, and we cannot simply calculate the average quantity, average reaction rate by average mass fractions and average temperature. That is not possible. So therefore we need to resort to one of the models like the flamelet model, conditional moment closure, and PDF method. So this we can use that. So here is a schematic. This is basically the gaseous phase. So we have a jet and we have a co-flow, and jet is bringing the fuel, the mixture fraction is 1 here, and the air is having a mixture fraction equal to 0. And if you plot at different locations the mixture fractions versus the scalar quantities like temperature and OH mass fractions, okay, then you can get a trend, right. So these are the scatter plots. If you measure instantaneously at different locations, you see the scatter plot like this. Now if you try to construct a fitted line through this, then this is basically the conditional average that we are getting. Okay. So this is the conditional average of temperature. Similarly, you can calculate the conditional average of the OH mass fractions also, and you see that with the experiment how it behaves. Okay. So what we have found that the fluctuation in the gas phase scalar quantities like the temperature and the composition, they are related to a fluctuations in a conserved scalar, right. So if locally there is some change in the temperature and the composition, that can be related to the fluctuation in the conserved scalar, that is mixture fraction. Okay. So that is the beginning of the presumed PDF approach. So where we are trying to link the fluctuation of a of the scalars with the fluctuation of a single conserved scalar, right, and that is how we are simplifying. So we have seen that already. So but here the question is that the mixture fraction is not a conserved quantity, okay, for sprays. So what do you do? So we can define the mixture fraction now based on the instantaneous quantities. Okay. And if it is defined instantaneous based on the instantaneous quantities, then it is always conserved. Okay. Mixture fraction is always conserved within the spray, and it will be conserved outside of the spray also, right. Within the spray, the mixture fraction could be unity, and if you go away from the spray, it will have some value in the gas phase. Okay. So, but it will be conserved instantaneously. Then from the instantaneous mixture fraction equation, we can average it, that is the phase averaging, and we can try to get the mean and variance of the mixture fraction. Okay. These are the transported equation of the mean and variance of the gas of the mixture fraction. Okay. Now the question is, how does gas phase scalar fluctuation affect droplet evaporation and heat and interface heat and mass transfer rate? Okay. As we have seen that in a turbulent flow there is a fluctuation in the velocity that has already been considered, but so far the fluctuations in the temperature and the composition were never considered in the mixture in the droplet evaporation case. Okay. But we know in a flame these quantities also vary very wildly. Okay. So in our models we should have some means to account for these fluctuations of temperature and the concentrations. Okay. So these are the two key questions which I am trying to address now. So this is part of my PhD work and the postdoc work. So I will continue that. Also the envelope flame. Okay. So if there is a, we have seen earlier, I have explained that if there is a flame, then the gradient of temperature increases very rapidly. Okay. It is more than what we have if there is no flame. Okay. It increases. Okay. Now the question is that when we calculated the Spalding number, in the traditional model they considered as infinity. If you see the definition of the Spalding number, it is based on the conserved scalar defined between the droplets, defined the conserved scalar at the infinity and then subtracted it from the conserved scalar defined at the surface of the droplet, right. Now infinity, the temperature is different, T infinity, which could be like 300 Kelvin in some cases or maybe more than that, but here if you have a flame surrounding the droplet, then the temperature gradient becomes very important. Okay. Now this is the envelope flame and it is formed between the droplet and then the infinity. Suppose this is the grid point where you have the mixture fraction which is Z, okay, which is almost close to 0, let us say, okay, and here is a droplet which is having a mixture fraction equal to unity, right. Now between unity and 0 there will be the stoichiometry somewhere, but since the droplet is subgrid, we are not resolving the flame. Okay. Everything is happening within the cell. Okay. So this is the, let us say this is the center of the cell, this is the droplet. Okay. The droplet is having a mixture fraction unity, and in the cell let us say the mixture fraction is 0.01 or something like that. Now between 1 and 0.01 there will be somewhere the stoichiometry located, right, and we know that if there is a stoichiometry there will be a height, there could be a flame, right, unless it is quenched there could be a flame. Now how to consider this effect of this flame? So far I think there was not much study for the spray combustion where they considered the envelope flame. Okay. But this situation will not arise if this is richer than the stoichiometry. Okay. In this picture, the mixture fraction that is prevalent at the far field, right? Far field means this is the droplet, this is the far field. Okay. Within the, because the droplet is very, very smaller than the grid size, so this is the droplet and this is the far field, the center of the volume maybe. Okay. And here the mixture fraction Z is greater than the stoichiometric mixture fraction, right? So then there could be no flame, envelope flame. I agree with that. But if the mixture fraction is on the other side of the stoichiometric mixture fraction, then there is a flame, and we need to model that effect. Okay. So there are two cases, but here due to the envelope flame, heat transfer rate increases. That is not the case there. The gradient is much smaller there. Here the gradient increased due to the envelope flame. Okay. So, somehow we need to account that in our model. Okay. So, now I will come to the Rance and LES of spray combustion. So, these are the governing equations for the liquid droplets. So, first we have the change in droplet location. So, dx dt equal to v, right, change in droplet velocity. So, this is the Vp, the droplet velocity, and this is the drag force, and then the gravity. Okay. And the CD we know how to model it, and then we have the droplet Reynolds number. So, that will basically come here, and we can calculate the droplet drag coefficient, right. Now, the change in droplet mass, right, dm dt is equal to minus m dot, right, and this m dot, if you simplify, it will be like this. Okay. So, this is the droplet mass conservation, this is the droplet energy conservation. So, change in droplet temperature. Okay. So, the first part is the basically the heat that is coming to the droplet, second part is the latent heat, right. Okay. And m dot is negative, so that is why it will be subtracted basically. Okay. So, this is the change in droplet temperature, and then there are non-dimensional numbers like Nusselt number and Serud numbers. These are functions of the Reynolds number, Prandtl number, and Schmidt number, and there are the Spalding transfer numbers like BH and BM that you can calculate like this. Okay. In the Rance, after the Reynolds average Navier-Stokes equation of turbulent space, we are writing the gas phase equations. So, the continuity equation, momentum equation, kinetic energy, and this is a dissipation of kinetic energy, mean mixture fraction and mean variance of mixture fraction. So, these are the set of equations that we are solving, and most of you are familiar with this. So, there is these are the terms that we need to model, that is quite common to the gas phase combustion, or any gaseous phase, any flow, right, any turbulent flow. But these are the source terms that is arising due to the interactions between the two phases. Okay. So, S dot m is the rate of evaporation, and this is the rate of change in momentum due to the gas and liquid phase interactions. Same thing about the K equation, epsilon equation, and then mixture fraction equation and the variance equation, right. So, we started with the instantaneous mixture fraction equation, which did not have any source term, but if you normalize, if you calculate the mean by averaging, phase averaging, then you will be able to get the mean equation, and then if you subtract the instantaneous equation, the mean equation from the instantaneous equation, then you will get the variance equation. Okay. So, here you have a term that is the scalar dissipation, and we do not know what is the scalar dissipation will be when there is an evaporating spray. It is itself difficult when there is a gaseous, we are talking about the gaseous fuel, but when there is liquid fuel, it poses more difficulty. So, that is one of the challenge for the turbulent spray combustion. So, we do not know how the scalar dissipation will be for the liquid fuel. For the gaseous fuel also there is no consensus so far. Okay. The numerical modelers basically change the constant of the dissipation rate, and they try to solve and claim that okay, their result is best. But here when we have the liquid fuel, we have more difficulties. Okay, now these source terms you can calculate by averaging over the cell. Okay. And now the solution strategy. So, you initialize the flow variables, solve them in the Rance solver like rho, u bar, pressure, temperature, composition, K and epsilon, and then these variables you can feed it to the Lagrangian solver where you solve the droplet location, velocity, temperature and diameter. You have the injection of the droplets, and then you can calculate the instantaneous velocity by supplying K, and then you get the RMS, and then from that you can evolve. Similarly, the droplet evaporation model needs estimate of BM, BH and these things, and then you can calculate the droplet temperature and diameter. Okay. Now, one thing I will tell about the droplet instantaneous temperature, like the expression of this Spalding number, if you see, okay, so there is temperature, right, and there is the fuel composition. Now, which temperature you are going to use? Are you going to use the mean or the instantaneous one? So, ideally you should use the instantaneous temperature. Like here we have used the instantaneous velocity. Similarly, we should recover instantaneous temperature from the mean temperature somehow. So, what we can do, we can we know basically the mixture fraction and variance, right. So, between 0 and 1, so we can plot the PDF, probability density function of mixture fraction, right. So, let us say this is like this, okay, and from this we can pick. So, this will satisfy some mean and some variance that you have computed already in your CFD code, and you can plot the PDF, and from this PDF we need to identify a mixture fraction, okay. That is possible. We can generate a random number and try to identify a mixture fraction, okay. So, let us say this is the mixture fraction. So, this is the instantaneous mixture fraction that droplet experiences. For example, there are 3 droplets. So, the mean is this one, but they will have different instantaneous mixture fractions, okay, that satisfies this PDF, okay. So, once you know the instantaneous mixture fraction, you can calculate the temperature, because you know if you have the infinite fast chemistry, you know the flame structure, right. So, you know the mixture fraction. So, you can come to this point, and this is the instantaneous temperature, right. So far people have used the mean temperature. So, mean temperature and instantaneous temperature are different, right. So, we should use this instantaneous temperature in our model, okay. So, that is what can be done using the mixture fraction concept. So, if you solve for the mean and variance of mixture fraction, you can sample the PDF and get the instantaneous mixture fraction, and from that you can calculate the, you can get the instantaneous temperature and instantaneous composition also, right. The composition also you know as a function of Z, so you can get that. Okay, so we can iterate until it converges for the RANs, and then that is the solution. Now, in LES again we have the source terms. We know, we have already seen how to model them. So, there is the SciCell method of Crow that we have already shown in the previous slide, and then the subfilter stresses can be modeled like this. And then we have the mean and variance of mixture fraction equation. So, this is the mean mixture fraction equation, and this is the source term that is due to the evaporation, and that is basically equal to what we have here, right. So, S dot Z equal to S dot M, and then we can employ the algebraic model for variance. In LES, we generally do not solve for the variance for the gaseous phase, okay. The variance can be obtained from the algebraic model, right. So, algebraic model tells that the dissipation should be equal to the production of the variance, right. So, in the variance equation you have the temporal term, then advection term, on the right hand side you have the diffusion term, then you have the production term of the variance, and then you have the dissipation term. And so, now you are saying that okay, production and in the equilibrium production should be equal to the dissipation, and then you can come up with the model of the variance. So, we do not need to solve this, but we can obtain this if you know Z. But when you have spray, so this is your, okay, this is your exact transport equation of the variance, okay. So, the previous model which I have shown, that assumes this is 0, this is 0, I mean this is also neglected, this is also neglected, and then this term is equal to this term, okay. So, this is the dissipation term and this is the production term, okay. But now when there is evaporation, there is another extra term. So, if we cannot neglect that now at this moment, okay. So, that is true for the gaseous phase. At equilibrium this term will be equal to this term and we are good, but when there is a evaporating spray, there is additional source term which we cannot neglect, okay. Now, this term needs some, I mean this is the full form of this term, okay. So, it is shown here. You can see that this is the instantaneous mixture fraction, this is the rate of evaporation, okay, and we have a we need to average this term. Okay. So, modeling is difficult. Okay. So, group combustion, so I will not go through this. So, I will now quickly show some slides regarding the flamelet progress variable approach for the spray jets. So, here I have taken the Sydney spray burner, which is having a jet. Okay. So, here you have an ultrasonic nebulizer which produces droplets, they are being convected here and they emerge out of this. So, during this pipe, actually when they are traveling, they are evaporating. Okay. So, at the end of this pipe you are getting a mixture of liquid ethanol and the vapor ethanol and the air, okay, that is coming out, and that is surrounded by a pilot flame here. So, this is a pilot flame, okay, and everything is put into a co-flow. Okay. So, co-flow has some velocity. Okay. So, all the parameters are listed. The stoichiometric mixture fraction is 0.1 for ethanol. So, some of the initial conditions we have. So, actually they have measured the inlet distributions and the distributions of the temperature distributions at different downstream locations. So, we can use our model and try to validate the results. So, I said this already, this thing that so now these are the equations which we solved. Okay. So, now the source term in the Z variance equation. So, this is the exact form of this and we need to compute this. So, what we have done that, this is the liquid which is having Z is equal to 1 and here you have the far field. Okay. So, now this source term S dot M is 0 within the liquid droplet, right. So, within that, if you are within the liquid droplet, there is no source term, right, there is no evaporation. If you are in the gas phase, the source term is also 0, right. So, source term is present only at the interface between the liquid and the gas phase, right. So, it is non-zero only at the interface, right, at Z equal to Z surface, right. We can calculate Z surface if you know fuel mass fraction at the surface. So, there at S dot M is non-zero, everywhere else it is 0. Okay. So, what I can do is that when I need to calculate this, I am replacing this Z by the Z surface here, okay, and then this is Z surface square just like this, and this is your rate of evaporation that we have already summed up over the volume. Okay. So, this is the source term. So, this is one model that we have used. Okay. Now, in flamelet progress variable approach, we have a tabulated the chemistry in terms of the mean and variance of mixture fraction and then the mean reaction progress variable, and then we can, if we compute this in our CFD cells, and then we recover the temperature as a function of these parameters, right. Then this is basically the algorithm. So, here we are solving for the filtered variables here, okay, and then we are supplying that to the Lagrangian solver and it is giving us the two phase source terms that we need here to solve the transport equations. Okay. And then we have the tabulated chemistry. So, we are sending the mean and variance of mixture fraction and the mean reaction progress variable, and it is giving us the composition and temperature and the reaction rate density. Okay. So, these are supplied to the Navier-Stokes solver. So, gas phase equations we have already seen, and then Lagrangian equations we are familiar with this now, and these are some of the results for these spray flames. You can see that the droplets are here actually, and you can see the high temperature flame and they are almost extinct here, only very few droplets are seen here, two cases. And then when I plot the results, I get somewhat good agreement with the trend, but at locations they are not matching, because within the R by D1 actually there is the spray. Okay. So, now we modeled the scalar dissipation rate, okay, and we did not consider the effect of the evaporating droplet because there is no model. So, we have used the classical model that is used for the scalar dissipation rate, and maybe that is the reason. So, you see the disagreement is more prominent near these regions, right, not here. In the outer layer it is perfectly all right, but when there is a spray within this R by D equal to 1, there we have some problem, but otherwise it is okay. So, some of the other parameters which I have shown here. Okay. So, here actually we have considered the scalar fluctuations, okay, and we have also utilized the unified mixture fraction that is applicable in the both gas phase and the liquid phase. So, the mixture fraction is defined based on the instantaneous quantity. Okay. Now, conditional moment closure method for sprays. So, in what is CMC? So, here actually we solve for the, in the flamelet model we do not include any transient effect, right, but there is unsteady flamelet method and probably we can do that, but in CMC method we relax some of the problems that is available, that is there inherently there with the flamelet model. Okay. So, we will basically solve the transport equation for the conditional scalars at each physical locations. Okay. So, conditional scalar means like the conditional temperature, right. Here you see that the infinite fast chemistry for the temperature, right. For the equilibrium, you know that it will be something like this. Okay. Now, you need to solve this, you are not solving in the flamelet, you are solving once and storing in a tabulated form, but in CMC at all grids we need to solve this profile over the time. Okay. So, that is the one difference between the flamelet and CMC method. So, here we are directly solving the temperature as a function of Z. Okay. So, this is the mean temperature as a function of Z, we are solving a transport equation of that. Okay. And then there will be the reaction rate source term on the right hand side, okay, and this is also function of Z. Okay. Now, this you can approximate as a function of conditional mean temperature and conditional mean species composition. Okay. So, if you know the mean conditional mean temperature and conditional mean species mass fractions, then you can calculate the reaction rate, conditional reaction rate, and now this conditional reaction rate can be utilized here and you can solve for the temperature. Same thing you can do for the species composition also. So, I will show the conditional moment closure equation in the next slide. Okay. So, what we are saying that this is the instantaneous quantity, right, and then we can split this, so this is the mean quantity and this is the instantaneous quantity y alpha, and we are splitting it into the mean plus conditional fluctuation, right. So, this is the mean quantity and this is the conditional quantity. The condition, this is the mean mean quantity, this is a fluctuation, right, around the conditional mean. Okay. So, now we are expressing this as a transport equation here. Okay. So, this is the temporal term of the conditional scalar and this is the advection term and you have a diffusion term, okay, and then you have the scalar dissipation rate term and then you have the chemical source term, you have the conditional evaporation rate source term and the conditional joint fluctuation of evaporation term. So, right, because it is conditioned on, so suppose we have a flame, okay. So, you are measuring at this point temperature and mixture fraction, let us say, and you have recorded your data, and when you plot it you see a scatter something like this. Okay. Now, conditional mean is this, it is expressed like this. So, now you need to plot a average line, a curve fit between all this data, let us say. So, this is the conditional mean. Okay.
We could just have called it the mean or average, right? Why do we call it a conditional mean?
Because it is conditioned on this variable. Suppose you are heating mixture fraction, let us say 0.3. Once you have a temperature 2200 Kelvin. Next time you come at 0.3, you have 2100 Kelvin. Next time you come at 0.3, and your mixture fraction is 2300 Kelvin. Okay, you can have this. Okay, now when you calculate the average temperature conditioned on mixture fraction 0.3, then it is 2200 Kelvin, right? Suppose you measure the mixture fraction and temperature at a particular location. So you have reached mixture fraction 0.3, but the temperature is different. So now temperature is 2200 Kelvin, next instance it could be 2100, and it could be 2300 in next time. Now you average when, I mean you also get some other numbers, like you get all sort of data. Now you try to average when you reached Z equal to 0.3, what is your mean temperature? So you reached mean temperature 2200 Kelvin, that is the conditional mean. So it is based on the condition that mixture fraction is 0.3 at that location, okay, and that is the average temperature whenever mixture fraction has reached 0.3, okay, and it is expressed T of Z, and this is the mean average. Okay, eta is basically the, it should be the sample space. I should write it in eta. So this is eta. Eta should be between 0 and 1, and this line is T of eta. Okay. So now we are trying to solve this profile every time instance. At every time step we need to solve for this T of eta. We start from some initial solution and we evolve in time. We are assuming the PDF. The PDF is given by the beta function. So if you know T of eta, and let's say if you have some PDF, okay, so you can calculate mean temperature. So mean temperature will be T of eta multiplied by P of eta d eta. So you have to carry out between 0 and 1. Okay. So then you recover the mean temperature and mean composition from this. Okay. So here you see that we have, when there is a two-phase flow, we have the conditional evaporation rate source term. So this pi of eta. So there is a paper by Mortensen and Bilger in 2009. There the theoretical development of the CMC method for multiphase flows are done. Okay. So I have used their framework, and I have taken these equations from that paper and tried to incorporate in my code, and I use that. So I need a model for this, and I need a model for the conditional scalar dissipation rate, and if they are available, then I can solve this and I can calculate T of eta, and then I can recover the mean temperature. So that is the idea of the CMC method. So some differences between the CMC and flamelet, so I am not going through that. So these are the models which I have taken for the mean scalar dissipation rate term, and this is the model for the mean evaporation rate. So I am assuming that whatever evaporation is taking place, it is evaporating at the droplet surface. That is true, right? So where the mixture fraction is Z surface. Okay. So it is a delta function at the Z surface. Okay. And then there is a coupling between the LES and the CMC solver. And when you know the conditional mean, so these are the conditional mean quantities, you are evaluating the Fabre mean quantities, and then you proceed like this. So there is a movie on the spray. I think the frame rate is very high here. So it is, here is a jet, and then it is surrounded by a pilot flame, and that is subjected in a co-flow. And you see that at pockets there is some extinction that is taking place. So locally the flame is getting quenched and then again reignited. So the conditional nomenclature method can predict this type of thing, which the other models may not be. Like the flamelet model cannot predict that things. So some of the comparisons which I will show, and yeah, so the temperature, the mean temperature with the experimental results at radial locations at different stations I have plotted. So it gives more or less good agreement. Now these are the liquid droplet statistics. So you see the droplet mean velocity, so mean radial and the mean axial velocity, and for different droplet size classes are plotted. So the droplet diameter less than 10 micron I have sampled, and then I have compared with the experimental results, and between 10 and 20 micron, 20 to 30 micron, and we see that fairly good agreement in all these axial locations. Okay. So this is the RMS velocity, U prime and V prime for the liquid droplet. So these are, I have collected the samples over a lot of time and then averaged it. Okay. These are the averaged result over some time interval. So it shows good agreement. Similarly, the droplet shorter mean diameter and the mean diameter. So the mean diameter is showing some deviations, but the shorter mean diameter is very close to the experimental results. So liquid volume flux. So here actually we tried to evolve from the Mortensen and Bilger CMC equations for the multiphase flows, and model the conditional evaporation rate and the conditional scalar dissipation rate, and the predictions are reasonably okay. So yeah, so that is the conclusion. So thank you. So I have tried to cover some part of the conditional moment closure method, but it may not be adequate. So if you have additional questions, then I can discuss that during your stay, or you can ask now.